things that might be helpful to know or to memorize, and we'll do a little bit of sketching as well. And for everybody else, I hope that you find this nice and relaxing. I hope that you feel free to just zone in and out as you please. There's no pressure at all. Hopefully you'll catch a tingle or two, or maybe just relax and get bored or fall asleep. It's all okay, and it doesn't matter whether or not you consider yourself to be a math person. It's all okay here. It's all okay. It's all okay. I just hope that you can sit back and enjoy, okay? Okay, so the normal probability distribution has a nice, pretty shape with it, and it's nice and symmetric, and it looks like a bell, and so some people literally call it a bell curve, and like a ring-a-ling, ding-a-ling bell, or like the notification bell if you clicked that, if you're subscribed to this channel. But yes, indeed, it looks like a bell, and the shape of it depends on mu and sigma, where mu is the mean and sigma is the standard deviation. So it's nice and symmetric about mu, so that midline or that highest part of the bell is mu, and the standard deviation has to do with how wide or narrow this bell is. So this is associated with the probability density function. So we're talking about the area underneath this curve. And if you have taken calculus before, it's okay if you haven't, but if you have, then when I mention the area underneath the curve, you might think of integrals. And yes, indeed, there is a density function that we can directly use, and use that alongside integrals to calculate probabilities. But if you're in like a first statistics class or AP stats, you probably don't really need to do this. But it exists, and I'll read it out for the math ASMR. So the probability density function P of x is 1 over sigma times the square root of 2 pi all times e to the power of negative x minus mu squared over 2 sigma squared. I had to write that down in such a crazy long function. The point is that it does exist, and it does take in a mu and a sigma. So basically the total area underneath this bell curve is 1. So all the way, but this bell does open from negative infinity to infinity, so that total, it's a continuous function, and it continues from negative infinity to infinity, but that total area is going to be 1. is going to have an area of 0.997, which means that if the total area is 1, the two little tails there have an area of 0.003. But those tails continue on and on and on because it goes from negative infinity to infinity. So your actual, it gets really, really small and basically negligible. It basically becomes negligible, but staying with 99.7% chance of being within 3 standard deviations, that covers most of it, right? And so the 68%, 95%, and 99.7% are 3 numbers that are extremely important and will probably come in handy over and over again when you do hypothesis testing or confidence intervals and that kind of thing. But we just have to know how to actually apply it. Okay, so 68% probability to be within 1 standard deviation, 95% probability to be within 2 standard deviations, and 99.7% probability to be within 3 standard deviations from the mean. So we can standardize all of this by setting mu equals 0, so our mean to be 0 and a standard deviation to be 1, so that when we draw this out, we'll have 0 and then 1, 2, 3, and -1, -2, -3. And this way, this is the z distribution, and this is where we can work with z-scores and our z-table and all of that. That's a whole other topic that we can get into, but basically if we have a random sample, then we can calculate its z-score based on the mean and the standard deviation, and z equals that sample minus mu over sigma. In other words, we're finding how many standard deviations away from the mean we actually are, and then we can use a z-table to actually find the probabilities. So this standardizes it all based around a mu equals 0 and a standard deviation of 1 instead of just whatever mu we wanted. But I hope that this is a nice little introduction to that. I'm going to go ahead and flip our camera down and sketch out this bell curve just to put some numbers and some visuals with this, but I hope that you're nice and relaxed right now, regardless. And if you are already asleep, I'm wishing you sweet, sweet mathy dreams. I'm going to do a little bit of sketching and then I will say good night, okay? So I am going to try to sketch this out so that you can get what I mean. I'll get it mean. So this isn't going to be perfectly symmetric, but that's alright. There we go. This is my bell curve. Ding dong, ding dong. It is centered about mu, which is my mean. In this case, I'm not going to standardize it, but if I were, mu would be 0 and sigma would be 1, right? So the total area under this thing is 1. necessarily a reason to have to calculate all this, except to just see it, which is cool. But also sometimes when working with z-score stuff, sometimes the way that we have to interpret the probability is a little weird, because sometimes there's a particular form, like a left tail, or you only look at values that are left of a certain value. So you kind of have to do this kind of reasoning anyway, so it's kind of a good habit to do, try out. But really it just comes from these three values again. So don't memorize this. Let's move one more standard deviation out. So 3 away, and you can see that we really are covering a lot of this area. Not the whole thing, because this goes from negative infinity to positive infinity, but a huge part, so 99.7%. So by the time you get to 3 standard deviations away from the left or the right, you're at 99.7%. So we can just fill in this last little area here, this little bit. You can see that it's getting smaller and smaller. So at first, going from 1 standard deviation to 2 goes from 68% to 95%, but then going one more standard deviation is much less of a difference. So we can do 0.997 divided by 2, and then subtract the 0.34 minus the 0.135. Okay, so 0.0235. So we can literally see that this area decreases as the marginal, the extra area is getting smaller and smaller. But if we added all these numbers together, we should get 0.997. And then that leaves us with this little tiny tail, and it should keep approaching. So it should be this little, really small. And these two tails account for 0.3%. So that would be 0.003 divided by 2. So that would be 0.0015. 0.0015. So you see that these areas are getting smaller and smaller here. So that's what these percents mean. So as far as standardizing this goes, basically we're going to translate all of this into z-score stuff. So this would be a z-score of 0. This is a z of 1. If this is a z of 2, z of 3, basically your z-score tells you how many